Deep in the cosmic dark, far beyond what our eyes can see, exist stars so massive they defy belief. We're not just talking about big, we're talking about giants that make our sun look like a grain of sand on a beach. But it's not just their size that's mind-boggling. These supermassive stars, living in the most extreme corners of space, behave in ways that completely baffle scientists. They're cosmic enigmas, performing actions and possessing properties that shatter our current understanding of stellar evolution and the universe itself. Today, we're diving headfirst into the strangest, most baffling aspects of these celestial behemoths as we explore 30 of their most peculiar behaviors. Our first strange behavior, their sheer, unbelievable brightness. Imagine a single star shining with the power of thousands, sometimes even millions of suns combined. Supermassive stars aren't just bright, they are blindingly luminous, pushing out so much energy they can rival the light from entire galaxies. This isn't just a little extra shine, we're talking about an energy output that seems impossible for a single cosmic object. What makes them so luminous? It boils down to their colossal size and scorching temperatures. The bigger a star, the more fuel it has to burn, and these behemoths burn through it at an unimaginable rate. Their interiors are furnaces unlike anything we can comprehend, generating incredible heat and pressure. This intense internal activity drives a phenomenal flow of photons, the particles of light, outward. Think of it like a colossal fire. The bigger the fire and the hotter it burns, the more light and heat it radiates. From relatively nearby, one of these stars wouldn't just be a bright point in the sky. It could potentially dominate the entire night and even day, casting shadows unlike anything we've ever experienced on Earth. Take, for instance, the star R13601, located in the Large Magellanic Cloud. This single star is estimated to be hundreds of times more massive than our Sun and emits over 7 million times more light. Another example is Pistol Star, which is also incredibly luminous, though not quite as extreme as R13601. Compared to our relatively modest Sun, which is a steady, predictable source of light and warmth, these supermassive stars are cosmic spotlights, burning with a ferocity that completely rewrites the rules of stellar physics. Yet, despite their generally blinding brilliance, these colossal stars come with another peculiar quirk. Their brightness isn't always steady. Imagine a light switch being flipped on and off, but on a cosmic scale with the most powerful light source you can imagine. Supermassive stars can exhibit dramatic, unpredictable variations in their light output, sometimes brightening considerably and at other times dimming, all seemingly without a clear pattern. This erratic behavior isn't like the gentle, predictable cycles of some smaller stars. Instead, it's more like a chaotic flicker, an intense, unstable dance of light that puzzles even the most seasoned astrophysicists. Why does this happen? One reason could be internal instability. These stars are so massive and hot that the pressure and energy churning within them aren't always in perfect balance. Think of a giant boiling pot. The bubbles aren't always the same size or appear in the same place. This internal turbulence can cause the star's outer layers to expand and contract, leading to pulsations that alter its observed brightness over time. Another factor might be interactions with the material surrounding them. Supermassive stars are often located in dense, dusty regions of space. As they move through or interact with these clouds of gas and dust, the material can temporarily block some of their light, causing them to appear dimmer. Conversely, if they're pulling in material, the resulting friction and heat can cause a temporary surge in brightness. Modeling these complex, irregular fluctuations is incredibly challenging. Scientists use sophisticated computer simulations, but the sheer scale and intricate physics involved make predicting these stellar mood swings incredibly difficult. It's like trying to predict the exact path of every single leaf falling from a tree in a storm. There are simply too many variables at play. It's a reminder that even with all our advanced technology and understanding, the universe still holds many profound mysteries, particularly when it comes to these extreme stellar objects. Beyond their dazzling and sometimes flickering light, supermassive stars are also cosmic exhales of incredible power. Imagine a constant hurricane, but instead of wind, it's a torrent of charged particles streaming away from the star at millions of miles per hour. These are stellar winds on steroids, so potent they are capable of stripping away vast amounts of the star's material over surprisingly short periods, cosmically speaking. While our Sun has a stellar wind, it's a gentle breeze compared to the gales from these giants. The sheer mass of these supermassive stars means their gravity is immense, yet the radiation and pressure within are so intense that they can actually overcome this gravity at the star's surface, pushing material outwards with incredible force. These winds are largely composed of ionized hydrogen and helium, the primary building blocks of stars, but also contain traces of heavier elements forged deep within the star's core. What drives these powerful outflows? The intense heat and light generated in the star's interior play a crucial role. As photons, the particles of light, stream outwards, they interact with the atoms in the star's outer layers, essentially pushing them away. This radiation pressure is the primary engine behind the most powerful stellar winds. It's a delicate balance between the star's gravity trying to hold itself together and the internal pressure and radiation pushing outwards. For supermassive stars, the outward push is often winning this tug-of-war, resulting in these massive outflows. The impact of these powerful winds on their surroundings is profound. They carve out vast cavities in the interstellar gas and dust, creating beautiful and complex structures known as stellar bubbles or nebulae. These winds can also deposit heavy elements forged in the star's core into the surrounding space, enriching the interstellar medium and providing the raw materials for future generations of stars and planets. Think of the Carina Nebula, a vast cloud of gas and dust sculpted by the powerful winds from some of the most massive stars known to us, including the enigmatic Eta Carinae, which we'll talk about later. The energy injected into the galaxy by these winds can also influence star formation, sometimes triggering it by compressing gas clouds, and other times preventing it by dispersing the necessary material. These winds demonstrate that these stars aren't just passive balls of light, they are active participants in shaping their galactic environments. Think about how much material the Sun loses over its entire lifetime through its stellar wind, which is a relatively modest process. Now imagine a star shedding an amount of material equivalent to several Earth masses every single year, year after year, for millions of years. That's the astonishing reality of supermassive stars and their rapid mass loss. These cosmic Goliaths are essentially bleeding themselves dry at an incredible rate, constantly expelling vast quantities of their own substance into the surrounding universe through those powerful stellar winds we just discussed. To put it another way, in just a few thousand years, one of these stars can lose as much mass as our Sun contains in its entirety. This phenomenal rate of mass loss has profound implications for how these stars live and eventually die. It's like a giant on a cosmic treadmill, constantly losing weight, and this weight loss directly impacts its size, temperature, and even the way it evolves. A star that loses mass rapidly will evolve differently than one that holds onto its material. This shedding can significantly shorten its lifespan as it burns through its fuel and expels its outer layers at the same time. It also changes the star's chemical composition over time as different elements are brought to the surface and blown away. Measuring this rapid mass loss is incredibly challenging. Scientists use various techniques, including observing the light and radio waves emitted by the stellar wind and the surrounding nebula. However, accurately determining the exact amount of material being ejected is complex due to the intricate physics of the winds and the varying conditions in the interstellar medium. It's a bit like trying to weigh steam escaping from a kettle in a strong wind. It's difficult to capture and quantify precisely. Despite the challenges, understanding this rapid mass loss is crucial for creating accurate models of supermassive star evolution and predicting their eventual dramatic end, which we'll touch on later. Here's a paradox for you. The biggest, brightest stars in the universe are also some of the shortest lived. It feels counterintuitive, doesn't it? You'd think something so massive would last forever, but supermassive stars are the cosmic equivalent of burning a candle at both ends. While a star like our Sun is expected to shine for about 10 billion years, these giants burn through their fuel reserves in mere millions of years. That might sound like a long time to us, but on the grand timescale of the universe, it's just a blink of an eye. Why this incredibly short lifespan? It all comes down to their incredible mass and the physics of nuclear fusion. The more massive a star is, the stronger its gravity, which means its core is under immense pressure. This extreme pressure leads to incredibly high temperatures, forcing hydrogen atoms to fuse into helium at an astonishing rate. This process, nuclear fusion, is what powers stars, but it's also what consumes their fuel. Think of it like a massive furnace. The bigger the furnace and the hotter it burns, the faster it uses up its coal. Supermassive stars are the biggest, hottest furnaces in the cosmos, and they are incredibly inefficient with their fuel, burning through it at a voracious pace. They start with a tremendous amount of hydrogen, but their fusion reactions are so energetic and occur over such vast volumes within the star that they exhaust this fuel supply far more quickly than smaller stars. This rapid consumption of fuel means their main sequence lifetime, the period where they are primarily fusing hydrogen in their core, is dramatically cut short. They live fast, burn incredibly brightly, and then move rapidly through their evolutionary stages towards a spectacular and often violent end. It's a dramatic, almost reckless existence compared to the long, steady life of a star like our Sun. They are cosmic sprinters in a marathon, leaving a brilliant but fleeting mark on the universe before their inevitable collapse. Another bizarre characteristic of some supermassive stars is their tendency to pulse violently. Imagine the entire star, this colossal ball of plasma, rhythmically expanding and contracting, but not with gentle breaths. These are powerful, dramatic pulsations, sometimes changing the star's size by significant amounts and causing noticeable shifts in its temperature and light output. It's like the star is alive and breathing, but in a very unstable, almost chaotic way. These stellar heartbeats aren't always regular either. They can be intense and unpredictable, adding another layer to the mystery of these cosmic giants. What causes this rhythmic, sometimes violent, swelling and shrinking? It generally boils down to imbalances within the star's interior between the forces pushing outwards, like radiation pressure and thermal energy, and the force pulling inwards, which is gravity. When the star expands, the pressure inside drops, gravity takes over and pulls the material back in. As it contracts, the pressure and temperature increase, pushing the material outwards again. This cycle repeats, creating pulsations, but in supermassive stars, these pulsations can be particularly strong due to their immense size and energy output. There are different ways a star can pulsate. Some pulsate radially, meaning the entire star expands and contracts uniformly like a balloon. Others pulsate non-radially, where different parts of the star oscillate in more complex patterns, creating ripples on the surface. Think of ringing a bell versus sloshing water in a bowl. The exact modes and intensity of these pulsations depend on the star's mass, temperature, and chemical composition. Scientists use theoretical models, complex computer simulations based on the laws of physics, to try and understand these stellar oscillations. These models help us predict how a star of a certain mass and composition should pulsate, but observing the real-world behavior of supermassive stars often reveals deviations from these predictions, highlighting the gaps in our understanding. Visualizing these pulsations can be tricky, but imagine a balloon being repeatedly inflated and deflated rapidly, or the surface of a giant drum being struck, creating ripples that travel across it. Observing and understanding these violent pulsations provides valuable clues about the internal structure and dynamics of these extreme stars, helping us piece together their complex lives. Consider this: there's a theoretical speed limit for how fast a car can possibly go, based on its design and how much power it has. In a similar way, stars have a theoretical limit to how bright they can possibly shine, known as the Eddington limit. For supermassive stars, a truly strange behavior is that they often operate incredibly close to this ultimate luminosity cap. What exactly is the Eddington limit? Imagine a never-ending cosmic tug-of-war inside the star. Gravity is constantly trying to pull everything inwards, compressing the star. But the intense nuclear fusion in the core creates vast amounts of radiation, light, and other forms of energy that push outwards. The Eddington limit is the point where this outward radiation pressure perfectly balances the inward pull of gravity. If a star exceeds its Eddington limit, the outward force of radiation becomes stronger than gravity, and the star begins to expel its outer layers at an accelerated and potentially catastrophic rate. Supermassive stars, with their already immense luminosity, are constantly teetering on this edge. It's like standing right at the very boundary of a cliff, with just the slightest push potentially sending you over. Being so close to this limit has profound implications for their stability. It makes them incredibly sensitive to small changes in their internal processes. A slight increase in fusion rate or a minor shift in pressure can push them over the edge, leading to those powerful stellar winds and rapid mass loss we discussed. This close proximity to the Eddington limit is a key factor in their violent pulsations and their relatively short, dramatic lives. It's a state of extreme, precarious balance that smaller, less luminous stars never experience, highlighting just how fundamentally different these cosmic giants are. Now, let's talk about an ending that's so dramatic, it's still largely theoretical for the most massive of these stars, the pair instability supernova. Imagine an explosion so powerful it dwarfs even the standard supernova we observe. Some of the most massive supermassive stars are predicted to meet just such a fate. This isn't your run-of-the-mill stellar explosion. It's a completely different beast driven by truly bizarre physics happening deep within the star's core. Here's what might happen: as the star burns through its fuel, its core gets hotter and denser. In stars of a certain mass range, reaching specific extreme temperatures and pressures, something incredible occurs. Instead of just having high-energy photons, those light particles streaming around and providing support against gravity, some of these photons spontaneously convert into pairs of particles, an electron and its antimatter counterpart, a positron. Think of it as energy transforming directly into matter and antimatter. This pair production has a critical consequence. It effectively robs the core of the radiation pressure that was helping to hold it up against gravity. It's like suddenly removing some of the pillars supporting a building. With this support gone, gravity wins the battle and the core begins to collapse rapidly. This rapid collapse triggers runaway nuclear fusion reactions throughout the star, far beyond the controlled burning that happened during its lifetime. The energy released is absolutely staggering, ripping the entire star apart in an explosion that leaves no remnant behind: no black hole, no neutron star, just a vast expanding cloud of gas and dust enriched with the elements forged in the star's final moments. The scale of a pair instability supernova is almost impossible to comprehend. They would be hundreds or even thousands of times brighter than standard supernova, potentially visible across vast cosmic distances. The sheer amount of energy and heavy elements blasted into space would have a profound impact on the composition of interstellar gas and dust in that region, influencing future star and planet formation in ways we are still trying to fully understand. It's a theoretical, yet chillingly plausible, grand finale for the universe's most gigantic stellar residents. Now, here's another peculiar observation about some of these cosmic giants. When scientists look at their light through a spectroscope, which is like a cosmic fingerprint reader that tells us what elements are present, they sometimes find little to no hydrogen. This is incredibly strange because hydrogen is the most abundant element in the universe and the primary fuel for most stars, including our Sun. Its absence in the light spectrum of a supermassive star is a major red flag. What does this tell us? It strongly suggests that we're looking at stars that are either in a very advanced stage of evolution or formed under highly unusual circumstances. For a typical star, the outer layers visible to us are rich in hydrogen. If that hydrogen is gone or significantly depleted, it implies that the star has somehow lost its outer envelope. One explanation for this hydrogen deficiency is that the star has shed these hydrogen-rich outer layers through those incredibly powerful stellar winds we discussed earlier, or perhaps through interaction with a companion star in a binary system. Imagine a giant onion, and the outer hydrogen layers have been peeled away, revealing the inner layers composed of heavier elements like helium or even carbon and oxygen. Another possibility, though less common, is that these stars formed from material that was already depleted in hydrogen, perhaps in an environment where the gas had a different chemical makeup. This would be incredibly rare in the early universe, but could potentially happen in specific, unusual cosmic nurseries today. Compared to the vast majority of stars we see, which clearly show the unmistakable spectral lines of hydrogen, these hydrogen-poor supermassive stars represent a distinct and puzzling class. Their unusual composition is a powerful clue that they have followed a very different evolutionary path, one that involves dramatic mass loss or an unconventional birth. Understanding why they lack hydrogen is key to unraveling their history and predicting their future, which is likely to be even more dramatic than that of their hydrogen-rich counterparts. Adding another layer to their extreme nature, supermassive stars possess surface temperatures that are, frankly, scorching beyond imagination. While our Sun's surface is a balmy 5,500 degrees Celsius, these giants can blaze at temperatures 50,000 degrees Celsius or even higher. This isn't just a little warmer, we're talking about an increase by factors of 10 or more. This extreme heat is directly tied to their incredible luminosity and energy output. Think of it this way: the hotter something is, the more energy it radiates. A small candle flame emits some warmth and light, but a blast furnace radiates vastly more. Supermassive stars are like cosmic blast furnaces, radiating energy at a phenomenal rate because their surface temperatures are so incredibly high. This heat is a direct consequence of the intense nuclear fusion happening deep within their cores. The energy generated there is so immense that it effectively pushes outwards, heating the star's outer layers to these extraordinary temperatures. Measuring these extreme surface temperatures is no easy feat. We can't exactly send a thermometer to a star 50,000 light-years away. Instead, astronomers rely on analyzing the star's light spectrum. The color and specific patterns of light and dark lines within the spectrum act like a thermal signature, revealing the temperature of the star's surface. Different elements absorb and emit light at specific wavelengths depending on the temperature, so by studying these spectral lines, scientists can determine just how hot the star is. Instruments like the powerful spectrographs on large ground-based telescopes or space telescopes like Hubble and the James Webb Space Telescope are essential tools for this kind of analysis. Compared to the relatively cool surface of a red dwarf star, which can be just a few thousand degrees or even our Sun's respectable temperature, supermassive stars exist in a completely different thermal regime. Their high surface temperatures are a defining characteristic, a visible manifestation of the immense power and energy churning within these truly extraordinary cosmic objects. How do stars this big even form in the first place? It's one of the most profound mysteries in astrophysics. Think about it. To build a star hundreds of times more massive than the Sun requires gathering an unimaginable amount of gas and dust from the surrounding cosmic environment. And these stars form relatively quickly, at least on cosmic timescales. The puzzle is how matter can be pulled together so efficiently and so rapidly to create these giants. Traditional star formation theories, which work well for smaller stars like our Sun, struggle to explain the birth of these behemoths. They predict that as a forming star grows, its intense radiation pushes away the surrounding material, effectively cutting off further growth. So, how do these supermassive stars overcome that powerful outward push to continue accumulating mass? Scientists have proposed several fascinating possibilities. One idea is that supermassive stars form through the merger of several smaller stars within dense star clusters. Imagine a cosmic demolition derby where stars collide and combine, incrementally building up to a supermassive scale. This scenario is plausible in the extremely crowded environments of some young star-forming regions. Another leading theory involves rapid accretion, where a protostar is able to pull in surrounding gas and dust at an exceptionally high rate, perhaps due to turbulent conditions in the parent molecular cloud or the absence of that radiation pressure wall we just mentioned at a critical stage. Instead of pushing material away, the environment allows for a continuous, massive inflow of matter. Observational evidence for both scenarios is actively being sought and debated. Finding direct evidence of stellar mergers is challenging but not impossible. Sometimes the aftermath of such a chaotic event leaves behind clues. Looking for regions with unusually high rates of gas infall onto young, massive objects could support the rapid accretion model. Each theory presents its own set of challenges and unanswered questions, and it's possible that different supermassive stars form through different mechanisms depending on their specific cosmic environment. The answer likely isn't a single one-size-fits-all explanation, adding to the depth of this cosmic riddle. Another layer of mystery surrounding these cosmic giants involves their magnetic fields. Think of the Sun's magnetic field, which causes sunspots and solar flares. Now scale that up exponentially to a star hundreds of times the size. What are the magnetic fields of supermassive stars like? Frankly, we don't entirely know. Directly measuring the magnetic fields of stars so distant and so powerful is incredibly challenging. Even with our best telescopes, it's difficult to get the precise data needed to map these fields accurately. However, what little we can infer suggests that if these stars possess strong magnetic fields, they could have a dramatic impact on some of their peculiar behaviors. Imagine those powerful stellar winds we talked about. A strong magnetic field could act like a cosmic cage, channeling those winds into specific directions or accelerating particles within them to even higher speeds. This could create complex, non-uniform outflows of material, potentially explaining some of the clumpy or structured nebulae observed around these stars. A powerful magnetic field could also influence the star's rotation. Just like how the Sun's magnetic field acts as a brake, slowing its rotation over time, a supermassive star's field could play a significant role in how fast or slow it spins. This rotation, in turn, impacts the star's internal structure and stability. For instance, rapid rotation might help counteract gravity to some extent, potentially influencing the star's lifespan or how it explodes. The lack of direct measurements makes this area ripe for theoretical speculation. Could unusually strong or unusually weak magnetic fields be responsible for some of the most extreme mass loss events or the strange variations in brightness? Perhaps these fields play a role in triggering those violent pulsations. The potential influence of magnetic fields on processes like core collapse and the eventual supernova outcome is also a hot topic of research. It's an area where our current observational capabilities are pushed to their limits, leaving a vast and intriguing gap in our understanding of these magnetic behemoths. These colossal stars aren't just isolated pinpricks of light. They are cosmic powerhouses that wield immense influence over the galaxies they inhabit. Think of them as cosmic architects, their lives and deaths profoundly shaping the evolution of the vast stellar cities they call home. Their impact comes mainly from two powerful forces, those relentless, powerful stellar winds we talked about, and their eventual, explosive demise as supernova. The continuous torrent of material expelled through their winds, and the even more dramatic explosion at the end of their lives, inject vast quantities of energy and, crucially, heavy elements into the surrounding interstellar medium, the gas and dust between the stars. These heavy elements, forged in the intense heat and pressure within the star's core, include elements like carbon, oxygen, iron, and many others that are essential building blocks for planets, moons, and even life itself. Without the cosmic alchemy performed by massive stars and distributed by their winds and explosions, galaxies would remain sterile collections of hydrogen and helium. This enrichment process isn't just about providing building materials. It also changes the chemical composition of the gas clouds, influencing how they cool and collapse, which in turn affects where and how new stars are born. But the influence doesn't stop there. The sheer energy released by supermassive stars, both through their winds and supernova, can act as a powerful force within the galaxy. The expanding shells of gas from supernova can compress surrounding gas clouds, triggering a new wave of star formation. Imagine a cosmic snowball effect where one star's death helps to create brand new stars. Conversely, this energy can also disperse or heat gas clouds, preventing them from collapsing and thus suppressing star formation in certain regions. It's a delicate cosmic dance of creation and destruction driven by the most massive stars. We see evidence of this influence throughout the universe. Take the stunning bubbly structures in star-forming regions like the Carina Nebula, carved out by the powerful winds and explosions of the massive stars within them. Or consider the distribution of heavy elements in galaxies. The abundance of elements heavier than hydrogen and helium increases over cosmic time, a direct result of generations of massive stars living and dying. The active galactic nuclei, the bright centers of many galaxies, might also be influenced by the presence and activity of massive stars near the central supermassive black hole. So, these supermassive stars aren't just interesting in themselves. They are fundamental drivers of galactic evolution, sculpting the landscape and providing the ingredients for future cosmic structures. It might seem obvious that something so vast and powerful would be spinning rapidly like a giant top in space. But when it comes to the rotation rates of supermassive stars, things get a bit complicated and often quite slow. Think about a figure skater pulling their arms in to spin faster. Conservation of angular momentum dictates that as something shrinks, it spins up. Protostars, the precursors to stars, form from vast, collapsing clouds of gas and dust that are often rotating. As this cloud shrinks and condenses to form a star, that initial rotation is expected to intensify significantly. For less massive stars, this leads to respectable spin rates. However, for supermassive stars, despite starting from rotating clouds, the expectation is often that they should end up spinning relatively slowly compared to their size. Why the slowdown? One major reason is their incredibly powerful stellar winds. Imagine those forceful outflows of material we discussed earlier also carrying away some of the star's angular momentum, effectively acting like a cosmic brake. It's like spinning a pinwheel and then blowing strongly on it. The air hitting the blade slows its rotation. Another factor could be internal processes that transfer angular momentum from the core outwards, perhaps through turbulence or magnetic fields, further contributing to a slower surface rotation. This slower spin, or in some cases a surprisingly fast spin, can dramatically influence the star's shape and stability. A rapidly spinning supermassive star wouldn't remain perfectly spherical. The centrifugal force at its equator would cause it to bulge outwards, taking on a flattened, oblate shape like a cosmic M&M. This distortion could affect the flow of energy within the star and even influence how it sheds mass. Observing the spin rates of these distant giants is another technical hurdle. Scientists use techniques like analyzing the width of spectral lines in their light. Faster rotation causes these lines to broaden due to the Doppler effect. While precise measurements are rare, studies of some massive stars, like those in the Tarantula Nebula, suggest a range of rotation rates exists, with some spinning faster than expected, adding another puzzle piece to the picture. Whether a supermassive star spins fast or slow has profound implications for its internal structure, its evolution, and the dramatic way it will eventually meet its end. Here's a mind-bending idea. What if some of these cosmic giants just vanished? We expect massive stars to end their lives in spectacular supernova explosions, but there's a fascinating possibility that the most massive of the supermassive stars might skip the explosion altogether and collapse directly into a black hole without a visible bang. Imagine a star dimmer than usual, perhaps pulsating strangely, and then simply disappearing from the sky. This is the concept of a direct collapse black hole, or more dramatically, a failed supernova. So, what conditions could lead to such a non-event, at least from our perspective? It all hinges on the star's core and how it handles the immense gravitational forces at play. As the supermassive star burns through its nuclear fuel, its core gets denser and hotter. Eventually, the core runs out of fuel it can readily fuse. At that point, there's nothing left to counteract the crushing force of gravity, and the core begins to collapse inwards at incredible speed. In a typical supernova, this collapse triggers a rebound, sending a shock wave outwards that blows the star apart. However, for the most massive stars, the core might be so massive and the gravitational pull so strong that even the shock wave can't escape. Instead, it might stall out and fail to propagate through the rest of the star. All that infalling material, instead of being expelled outwards, just keeps piling onto the collapsing core. This runaway accretion of mass rapidly increases the density at the center, and gravity quickly overwhelms all other forces. The core collapses in on itself, forming a black hole almost instantaneously. The outer layers of the star, lacking the explosive push from a successful supernova shock wave, might simply fall back onto the newly formed black hole or be expelled in much weaker outflows that are far less luminous than a supernova. The implications of this failed explosion are profound. It means that some black holes could be forming in the universe without leaving behind the bright, telltale signature of a supernova. This has significant consequences for how we estimate the rate of black hole formation in the universe. If a significant fraction of the most massive stars end this way, our current estimates might be low. Furthermore, the formation of a black hole from a collapsing star is a cataclysmic event that creates ripples in space-time called gravitational waves. Detecting gravitational waves from these direct collapse events, which current and future detectors might be able to do, would provide direct evidence for this alternative path to black hole formation and offer unique insights into the physics of gravity in its most extreme form. It's a powerful reminder that even in the violent deaths of stars, the universe holds subtle, unexpected processes that continue to challenge and expand our understanding. Imagine the universe when it was just a baby, a couple of 100 million years old before the first galaxies had fully formed. This was a very different place, a dark age filled primarily with hydrogen and helium. But something had to kickstart the process of building stars and galaxies as we know them. This is where supermassive stars potentially played a truly foundational role. Scientists theorize that the very first stars to form, known as population Roman III stars, might have been incredibly massive, perhaps even more so than the supermassive stars we observe today. Why so massive? The conditions in the early universe were different. The gas clouds from which these stars formed were purer, lacking the heavier elements that act as coolants in modern star formation. This lack of cooling meant that bigger clumps of gas were needed to collapse and form stars, leading to these potentially gigantic first-generation stars. These theoretical early supermassive stars would have been incredibly hot, luminous, and short-lived, burning through their fuel in just a few million years. But their impact would have been profound. Think about that reionization of the universe. For hundreds of millions of years after the Big Bang, the universe was neutral, with electrons and protons mostly existing as separate particles. The light from these first stars and the early quasars, thought to be powered by supermassive black holes, would have been energetic enough to strip electrons from atoms, essentially reionizing the universe and making it transparent to light. This was a pivotal moment in cosmic history, and supermassive stars might have provided a significant portion of the energy needed to achieve it. Studying the faint light from the most distant galaxies and searching for the signatures of these early stars remains one of the most exciting frontiers in modern cosmology, a quest to understand our cosmic origins and the foundational role these massive pioneers might have played. Now imagine two giants dancing incredibly close together in space. When a supermassive star isn't alone but is part of a binary system with a companion star, things can get truly bizarre. Their immense gravity and powerful outflows mean interactions between them aren't subtle. They're dramatic and often lead to some incredibly strange behaviors. One of the most fascinating phenomena in these systems is mass transfer. If the stars are close enough, the supermassive star's gravity can actually pull material off its companion star, creating a swirling disk of gas around itself. This incoming material can heat up and emit X-rays, making these systems powerful sources of high-energy radiation that we can detect with specialized telescopes. Think of it like one star siphoning off the essence of its partner. This mass transfer isn't just a gentle flow, it can be a torrent, significantly impacting the evolution of both stars. Tidal forces, the gravitational pull exerted by one celestial body on another across its diameter, also play a huge role. These forces can distort the shape of the companion star, making it elongated, and can even influence the supermassive star itself, potentially triggering or affecting those pulsations we discussed earlier. And if the dance gets too close, the ultimate interaction can occur, a stellar merger. Two stars colliding and combining their mass is a cataclysmic event, releasing vast amounts of energy and potentially forming an even more massive, and perhaps even stranger, single star. These mergers are thought to be incredibly violent and could explain some of the most massive single stars we observe. We've seen compelling examples of these binary systems. Eta Carinae, a famous supermassive star, is believed to be part of a binary system, and the dramatic changes observed in its light over the centuries are likely influenced by its interaction with its companion. Other systems, identified through observations of X-ray emissions or unusual spectral signatures, hint at the prevalence of these dramatic stellar duets among the supermassive population. Studying these binary systems where supermassive stars are locked in a gravitational embrace offers unique insights into their properties and how they evolve under extreme conditions, adding another complex chapter to the story of these cosmic giants. Imagine a star suddenly coughing up a giant cosmic hairball. That's kind of what happens during what scientists call episodic shell ejections, another truly strange behavior observed in some supermassive stars. Instead of a steady, continuous flow of material like the regular stellar winds, these stars occasionally undergo sudden, dramatic outbursts, expelling huge amounts of gas and dust in relatively short bursts. It's like the star is holding its breath and then suddenly lets it all out in a powerful expulsion. Think of the famous star Eta Carinae again. It's a prime example of a supermassive star that has undergone incredibly powerful shell ejections in the past, most notably the Great Eruption in the 1840s, which expelled a mass equivalent to several suns and dramatically changed its appearance. So, what triggers these violent expulsions? It's likely tied to those internal instabilities and violent pulsations we discussed earlier. When the star's internal pressure and gravity are in a precarious balance, a particularly strong pulsation or a sudden surge in energy from the core could effectively blow off the star's outer layers. Imagine a pot of boiling water where a large bubble suddenly bursts on the surface, splashing water outwards. On a stellar scale, these bursts are powerful enough to overcome the star's immense gravity, sending vast shells of material hurtling into space. When these shells of ejected material expand outwards, they cool and condense, forming spectacular structures of gas and dust around the star, known as circumstellar nebulae. These nebulae can take on various shapes, sometimes appearing as intricate hourglass figures, bipolar outflows, or irregular clumps, depending on the geometry of the ejection and the surrounding environment. Studying the shape and composition of these shells helps astronomers piece together the history of the star's outbursts and understand the physics driving these dramatic events. Think of them as fossil records of the star's past tantrums. These shell ejections represent a significant loss of mass for the star, even beyond the regular stellar winds, and can dramatically alter its evolutionary path and its ultimate fate. They are a visible testament to the extreme, unstable nature of these cosmic giants. When a supermassive star finally reaches the end of its short, dramatic life, it doesn't go out quietly. It detonates in a supernova, an explosion so powerful it can briefly outshine an entire galaxy. But not all supernovae are created equal, and the most massive stars are believed to be the progenitors of specific, incredibly energetic types. Think of it like different flavors of cosmic fireworks, each tied to the kind of star that exploded. The most common fate for stars less massive than our Sun is a gentle fade into a white dwarf. Stars like our Sun will go through a red giant phase and eventually shed their outer layers, leaving behind a dense core. But for the giants we're discussing, those with masses many times that of the Sun, the end is far more violent. These supermassive stars are the leading candidates for what are known as Type Ib, Type Ike, and especially Type Roman II supernova. What separates these types? It largely comes down to what's in the star's outer layers when it explodes. Type Roman II supernova show strong spectral lines of hydrogen, indicating that the progenitor star still had its outer hydrogen envelope intact when it went boom. Type Ib supernova, on the other hand, show very little hydrogen but do show spectral lines of helium. This suggests the progenitor star lost its outer hydrogen layer before exploding, perhaps through those powerful stellar winds or interaction with a companion star. Type Ike supernova show very little hydrogen and very little helium, implying the star lost both its outer hydrogen and helium layers, likely revealing the deeper layers of heavier elements like carbon and oxygen before it exploded. Supermassive stars, particularly those in binary systems or those with incredibly strong winds, are excellent candidates for the progenitors of these hydrogen and helium-stripped supernova Type Ib and Ike. Their rapid mass loss explains how they could shed these outer layers before their final collapse. The most massive stars, those flirting with hundreds of solar masses, are specifically linked to the most energetic of these explosions, and as we discussed, potentially even those theoretical pair instability supernova, although those would be a distinct class of explosion. The sheer mass of the star dictates the energy of the explosion and the elements that are synthesized and ejected into space. More massive stars undergo more advanced stages of nuclear fusion in their cores, creating heavier elements, which are then scattered into the cosmos by the supernova. By studying the light curves, how the brightness of a supernova changes over time, and the spectra of these different supernova types, astronomers can piece together the nature of the star that died. It's a bit like forensic science on a cosmic scale, using the remnants of the explosion to understand the life and death of the star that caused it. Understanding which types of supernova come from supermassive stars is crucial for understanding the cosmic cycle of matter and energy and how heavy elements are distributed throughout the universe. Think about the gold in your jewelry, the iron in your blood, or the silicon in your phone. Where did these elements come from? The answer is one of the most profound and beautiful stories the universe has to tell, and supermassive stars are key characters in it. We're talking about the cosmic alchemy that happens deep within these stellar furnaces, nucleosynthesis. This is the process where lighter atomic nuclei fuse together under unimaginable heat and pressure to create heavier ones. During their relatively short lives, supermassive stars are hydrogen-burning powerhouses, fusing hydrogen into helium. But as their cores contract and heat up, they move on to fuse helium into carbon and oxygen, and then, in increasingly short and violent stages, they create elements like neon, magnesium, silicon, and eventually iron in their cores. Imagine an onion with layers of different elements being fused at different temperatures. The most massive stars go through more of these burning stages, building up a core of iron. What makes this process so important is what happens next. When these stars unleash their powerful stellar winds, they expel some of these freshly forged elements into the surrounding space. Even more dramatically, when they explode as supernova, they blast these heavier elements outwards with incredible force, enriching the vast clouds of gas and dust between the stars. This is how the universe gets seasoned, slowly building up the raw materials needed to form rocky planets, complex molecules, and ultimately, life. Without the nucleosynthesis and subsequent dispersal by supermassive stars and their less massive but still impactful cousins, the universe would still be a dilute soup of hydrogen and helium, a far simpler and less interesting place. They are the universe's element factories and scatterers, making possible everything we see and are. Beyond the presence or absence of hydrogen, the chemical makeup of supermassive stars can reveal even stranger secrets. Imagine analyzing the ashes of their powerful fusion reactions, finding unexpected ingredients mixed in. While all stars start primarily with hydrogen and helium, the elements they forge in their cores and the elements they pick up from their surroundings create a unique chemical fingerprint. For supermassive stars, these fingerprints sometimes show unusual abundances of certain elements. For example, we might detect surprisingly high amounts of nitrogen or sodium, elements that are typically less abundant in smaller stars. What does this tell us? It's like finding a foreign substance in a crime scene. It provides vital clues about the star's history. A high abundance of nitrogen could indicate that the star has gone through a phase where material from its core's nuclear burning has been mixed up to the surface through processes like convection. Think of it like stirring a pot, bringing the ingredients from the bottom up. Alternatively, unusual compositions could hint at the environment where the star was born. If the gas cloud from which the star formed was already enriched with certain elements from previous supernova explosions or the winds of other stars, the resulting supermassive star will inherit that peculiar chemical signature. Analyzing these chemical compositions is done by splitting the starlight into its component colors, creating a spectrum. Different elements absorb or emit light at specific wavelengths, creating a unique pattern of dark or bright lines in the spectrum. By carefully studying the intensity and position of these spectral lines using instruments called spectrographs, astronomers can determine not only which elements are present but also their relative abundances. It's a painstaking process, like deciphering a complex cosmic code. The Hubble Space Telescope and the James Webb Space Telescope, with their sensitive instruments, are invaluable for this kind of detailed spectral analysis. Compared to the relatively standard chemical compositions of most stars in our Milky Way, the unusual fingerprints of some supermassive stars stand out, suggesting unique evolutionary paths or unusual birth environments. These chemical oddities are powerful diagnostic tools, helping scientists piece together the life story of these enigmatic objects and the conditions in the distant corners of the universe where they reside. These cosmic giants don't just exist in isolation. They are sculptors of their galactic neighborhoods, particularly those vibrant, chaotic places where stars are born. Think of a dense nursery filled with gas and dust, the raw materials for new stars. The presence of a supermassive star in such a region can have a twofold, and sometimes contradictory, effect on the formation of its smaller siblings. On one hand, their intense radiation and powerful stellar winds can actually trigger star formation. Imagine massive jets of energy and material slamming into surrounding gas clouds. This collision can compress the gas, increasing its density to the point where gravity can take over and cause it to collapse, forming new stars. It's like a cosmic domino effect, where the energy from one massive star kickstarts the birth of many more. You see visual evidence of this in stunning images of star-forming regions, where bright knots of young stars appear in the wake of powerful outflows from central massive stars. These images, captured by telescopes like Hubble and the James Webb Space Telescope, paint vivid pictures of this energetic interaction, showing glowing pillars of gas and dust being shaped by stellar winds and radiation. However, these cosmic giants can also be disruptive forces. Their powerful winds and overwhelming radiation can also blow away or disperse the surrounding gas and dust, removing the very material needed to form new stars. If the stellar winds are strong enough and the gas clouds are not sufficiently dense or protected, they can be effectively sterilized, preventing further star formation in that area. It's like trying to plant seeds in a garden during a hurricane. The conditions are too volatile to allow delicate growth. This dual role, both triggering and inhibiting star formation, makes the influence of supermassive stars on their nurseries incredibly complex and fascinating to study. Understanding this interplay is crucial for comprehending how star-forming regions evolve and how galaxies build up their stellar populations over time. Trying to figure out just how far away these supermassive stars are is a prime example of how tough studying them can be. Imagine trying to guess the wattage of a light bulb 100 miles away just by looking at how bright it appears. It's incredibly difficult because the apparent brightness you see depends on two things: how intrinsically bright the light bulb actually is and how far away it is from you. The same problem plagues astronomers looking at stars, especially those in distant galaxies. Measuring the distance to celestial objects is one of the fundamental challenges in astronomy, and for these incredibly remote supermassive stars, the usual tricks often fall short. Think about the parallax method, which works wonderfully for nearby stars by observing their apparent shift in position as the Earth orbits the Sun. That method is useless for stars in other galaxies because they are simply too far away for us to detect any measurable shift. So, how do we even begin to estimate the distance to these cosmic beacons? Astronomers rely on what are sometimes called standard candles. These are objects with a known intrinsic brightness, meaning we know how luminous they are regardless of their distance. If you know how bright something truly is, and you measure how bright it appears from Earth, you can then calculate how far away it must be. A prime example of a standard candle is a certain type of supernova called a Type Ia supernova. However, supermassive stars themselves don't fit neatly into this category, and while their explosions as supernova can act as standard candles, determining the distance to the living supermassive star before it explodes is a different challenge. For supermassive stars, we often have to rely on less direct methods, which introduce more uncertainty. If the supermassive star is part of a star-forming region or a galaxy whose distance has been estimated using other methods, we can assume the star is roughly at the same distance. But those initial distance estimates for the galaxy or region also have their own margins of error. We also look at things like the expansion of the universe. For very distant galaxies, their redshift shift in their light towards the red end of the spectrum caused by the expansion of space gives us an estimate of their distance. However, applying this to individual stars within those galaxies requires assumptions about the star's motion within the galaxy itself. The real kicker is that even small errors in distance measurements can lead to big inaccuracies in our understanding of a supermassive star's properties. Since apparent brightness decreases with the square of the distance, if you underestimate the distance to a star, you will also underestimate its true intrinsic luminosity. If you think it's closer than it is and it looks a certain brightness, it must be less powerful than if it were farther away. Conversely, if you overestimate the distance, you'll overestimate its luminosity and therefore its true power output. This propagates into estimates of the star's mass, radius, temperature, and even its lifespan. It's like trying to measure the size and power of that distant light bulb. If you think it's only 50 miles away when it's actually 100, you'll conclude it's much smaller and dimmer than it truly is. The inherent uncertainties in distance determination for these far-off giants mean that our understanding of their most fundamental characteristics contains a degree of imprecision, constantly pushing astronomers to refine their measurement techniques. Here's a truly mind-bending consequence of these stars' immense mass. They can actually warp the fabric of space-time around them. Think of placing a heavy bowling ball on a stretched rubber sheet. It creates a dip, right? In the universe, mass does something similar to space-time. For incredibly massive objects like supermassive stars, this warping is significant enough to bend the path of light rays traveling nearby. This phenomenon is called gravitational lensing, and it acts like a cosmic magnifying glass or a funhouse mirror, distorting the images of objects located far behind the lensing star. Imagine a distant galaxy positioned directly behind a supermassive star relative to our line of sight. The light from that galaxy travels towards us, but as it passes near the massive star, its path is bent by the star's gravity. This bending can do several things. It can magnify the image of the background object, making faint and distant galaxies appear brighter and larger than they normally would. It can also distort the image, stretching it into arcs or even creating multiple images of the same background object, appearing as a ring or several separate points of light around the lensing star. These bizarre ring shapes, known as Einstein rings when the alignment is perfect, are a direct and stunning visualization of space-time warping. How does this help us study supermassive stars or the objects behind them? By carefully analyzing the way the light from a background object is lensed, astronomers can deduce properties of the lensing star, even if it's too faint or distant to study directly in detail. The amount of bending is directly related to the mass of the lensing object. The stronger the bending, the more massive the star. So, gravitational lensing provides a way to weigh these massive stars using how they distort the light around them. It's like determining the weight of that bowling ball by measuring how deep of a dip it creates in the rubber sheet. Furthermore, these cosmic lenses allow us to peer into the distant universe and study objects that would otherwise be too faint to see. The magnification provided by the lensing effect acts like a natural zoom lens, bringing incredibly distant galaxies into view and allowing us to study their properties in detail, like their composition or how quickly they are forming stars. Some of the most distant and earliest galaxies ever observed have been discovered and studied using the magnification boost provided by gravitational lensing from foreground galaxy clusters, and individual massive stars can produce micro-lensing effects on a smaller scale. The phenomenon of gravitational lensing, predicted by Einstein's theory of general relativity, is a powerful tool in the astronomer's toolkit, providing unique insights into the mysterious lives of supermassive stars and unveiling hidden wonders in the distant cosmos. Now, let's talk about an even more powerful explosion than a standard supernova, something so energetic it's earned its own name, a hypernova. Imagine the most powerful bomb you can possibly conceive of, and then multiply its energy output by astronomical factors. Some of the most massive supermassive stars are theorized to end their lives in these absolutely mind-blowing events. What makes a hypernova different from a regular supernova? It's all about the energy released and the speed at which the stellar core collapses. In a typical supernova, the core collapses and bounces back, sending a shockwave through the star. In the case of a hypernova, which likely originates from a rapidly rotating supermassive star, the core collapses into a black hole, but this process is accompanied by the launching of incredibly powerful, focused jets of material outwards from the star's poles. Think of it like squeezing a tube of toothpaste with immense force. The paste shoots out in a narrow stream. These jets are traveling at speeds approaching the speed of light and carry a tremendous amount of energy. The energy released in one of these hypernova jets can be tens or even hundreds of times more energy than a standard supernova explosion. The conditions needed for a hypernova are thought to be quite specific. You need a star that is not only supermassive but also rotating very rapidly. This rapid spin is crucial because it helps to channel the energy of the collapsing core into those powerful jets. Without significant rotation, the core would likely just collapse into a black hole without launching such energetic outflows. One of the most exciting links to hypernova is their potential connection to long-duration gamma-ray bursts, the most luminous electromagnetic events known to occur in the universe. When one of those hypernova jets is pointed directly towards Earth, the intense beam of gamma rays it produces might be what we observe as a gamma-ray burst. These bursts are incredibly short-lived, lasting from a few seconds to a few minutes, but in that time they release more energy than our Sun will produce over its entire 10 billion-year lifetime. So, the next time you hear about a gamma-ray burst detected by our telescopes, remember that it might be the cosmic farewell of a rapidly spinning supermassive star collapsing into a black hole in a spectacular hypernova event, a truly rare and energetic phenomenon in the universe. Even with our most powerful telescopes, studying these distant giants is like trying to see individual leaves on a tree across a vast valley. The sheer distance and the limitations of our current observational tools mean that our view of the supermassive star population is likely skewed, introducing what we call observational biases. Think about it. What sort of supermassive stars are we most likely to detect? We're going to see the brightest ones first, the ones that shine with incredible luminosity, because their light is strong enough to reach us across those immense cosmic distances. This means we might be missing out on an entire population of supermassive stars that are either intrinsically less luminous, perhaps in a quieter phase of their lives, or are obscured by dust and gas in their home galaxies. It's like trying to survey the population of a city by only looking at the lights from the tallest skyscrapers at night. You're going to miss all the people living in the smaller buildings below or in less brightly lit areas. Similarly, our current telescopes are more sensitive to certain wavelengths of light than others. If a supermassive star emits most of its energy in wavelengths that our instruments aren't particularly good at detecting, we might completely miss it. For example, stars heavily shrouded in dust might primarily emit infrared light, which requires specialized infrared telescopes like the James Webb Space Telescope to observe effectively. This inherent difficulty in detection means that our current catalogues of supermassive stars might not be fully representative of their true diversity in the universe. We might be overcounting certain types, the brightest, least obscured ones, and undercounting others. Overcoming these biases is a major goal for astronomers. It requires developing new and more sensitive telescopes capable of observing across a wider range of the electromagnetic spectrum, from X-rays and gamma rays to radio waves, and also employing clever observational strategies to peer through obscuring dust or detect fainter objects. It's a constant effort to build a more complete and accurate picture of the supermassive star population, ensuring that our understanding isn't just based on the easiest ones to find. Trying to accurately simulate the lives of these behemoths on a computer is an absolute nightmare for scientists. Imagine building a virtual star from scratch, 100s of times more massive than our Sun, and getting all the physics right. The challenges in creating accurate theoretical models of supermassive stars are immense, pushing the limits of our computational power and our understanding of fundamental physics. Why so difficult? Their extreme properties mean that many of the approximations and simplifications that work for modeling smaller stars simply break down. You have to factor in incredibly complex processes happening simultaneously. For instance, those violent pulsations mean you can't treat the star as a perfectly stable sphere. You need models that account for dynamic changes in size and shape. Then there's the powerful convection happening deep inside, like a turbulent boiling motion on a cosmic scale, efficiently transporting energy outwards. Modeling this turbulent flow is incredibly complex, often requiring three-dimensional simulations that demand enormous computing resources. And let's not forget rotation. If the star is spinning, you need to incorporate the effects of centrifugal force and how it redistributes mass and energy, which adds more complexity. Magnetic fields, although difficult to measure directly, are also thought to play a crucial role, influencing internal dynamics and those powerful stellar winds. But accurately modeling stellar magnetism is its own field of challenging research. And of course, the rapid, often episodic, mass loss we discussed must be included. But the physics of how material is expelled from such extreme stars isn't fully understood either. All these factors, convection, rotation, magnetism, and mass loss, are intertwined, influencing each other in ways that are difficult to untangle. Despite these challenges, these theoretical models are absolutely essential. They are the only way we can try to interpret the limited observational data we get from these distant objects. A theoretical model provides predictions for how a star with certain properties should look, how it should evolve, and how it should end its life. By comparing these predictions to what we actually observe with telescopes, scientists can refine their models, test different hypotheses about the star's internal physics, and eventually build a more complete picture of these cosmic giants. Without robust models, our observations would just be isolated pieces of a puzzle with no way to put them together. Now, let's consider an even stranger possibility for how some supermassive stars might end their lives, venturing into the realm of the hypothetical. We've talked about black holes and different types of supernova and their remnants like neutron stars. But what if, just what if, some of these most extreme stars evolve into something truly exotic? Imagine a star that's not just a massive ball of hot gas, but something that's got a dense, super-compact object lurking at its very core. This is the idea behind theoretical objects like the Thorne-Zitkow object. Picture a red supergiant or a blue supergiant star, colossal in size, but instead of a normal stellar core where fusion is happening, it somehow encompasses a neutron star. A neutron star, remember, is the super-dense remnant of a smaller supernova, packed with the mass of our Sun but squeezed into a sphere only about the size of a city. The concept is that in a binary system, if a supermassive star swells up and engulfs its neutron star companion, the neutron star could spiral inwards and settle at the center of the larger star. The physics of such a hybrid object would be incredibly complex. The neutron star's immense gravity would interact with the surrounding stellar material, leading to unusual nuclear reactions and potentially influencing the star's outward appearance and behavior in weird ways. Other, even more speculative possibilities exist for the end states of the most massive stars that don't quite make a black hole or a standard neutron star, potentially leading to remnants with properties unlike anything we've definitively observed. These ideas are firmly rooted in theoretical physics and are based on extreme scenarios and the behavior of matter and gravity under conditions we can only simulate in computers or probe indirectly through rare observations. They represent the bleeding edge of astrophysical speculation, born from the need to explain some of the truly puzzling phenomena we sometimes glimpse in the cosmos. For now, Thorne-Zitkow objects and other such exotic remnants remain largely theoretical, cosmic unicorns that we are actively searching for observational evidence of. Detecting one would be a monumental discovery, providing unprecedented insights into the physics of matter under the most extreme conditions and potentially revolutionizing our understanding of stellar evolution. It's a powerful reminder that even after decades of studying stars, the universe still holds the potential for entirely new and unexpected forms of celestial bodies. These colossal stars aren't just powerful, they're cosmic actors engaged in a dynamic interplay with their surroundings, participating in what scientists call stellar feedback. Imagine a giant, complex system within a galaxy where the birth, life, and death of stars influence the very environment that gives rise to new stars. Supermassive stars are key players in this intricate feedback loop, their immense energy output and dramatic mass loss acting as powerful regulatory forces within the interstellar medium, the gas and dust that fills the space between stars. Their intense radiation and powerful stellar winds, those constant gales of charged particles, can heat and push away surrounding gas, preventing it from collapsing to form new stars. Think of it like stirring a pot of soup. The stirring motion prevents the ingredients from settling at the bottom. This is negative feedback where the star's activity inhibits further star formation in its immediate vicinity. However, these very same forces can also trigger star formation in other areas. When the expanding shells of gas from their powerful winds or eventual supernova explosions collide with denser clouds of gas and dust, they can compress that material, increasing its density to the point where gravity takes over and new stars begin to form. This is positive feedback where the star's activity actually promotes the birth of new stars elsewhere. Diagrams help us visualize these complex feedback mechanisms. Imagine a diagram showing a massive star in a gas cloud, with arrows illustrating the outflow of energy and material pushing on the surrounding gas. Another part of the diagram might show how these expanding shells then impact other clouds, leading to new centers of gravitational collapse and the formation of new stars. These processes aren't isolated events. They occur throughout a galaxy, influencing the overall rate at which a galaxy converts its gas into stars. If feedback is too strong and too widespread, it can effectively shut down star formation in certain regions or even across an entire galaxy, leading to a less active, red and dead galaxy that has used up or expelled most of its available gas. Conversely, a balance of feedback with both triggering and inhibiting effects helps to regulate the star formation rate, preventing the galaxy from burning through all its gas too quickly while still ensuring new stars are born over cosmic time. Understanding how supermassive stars participate in these feedback loops is crucial for understanding the evolution of galaxies, how they acquire their shapes, and how they build up their populations of stars over billions of years. They are not just points of light in the sky, they are essential drivers of galactic evolution, shaping the cosmic landscape in profound ways. Even with all the incredible insights we gain from splitting starlight into its spectrum, sometimes these cosmic fingerprints contain patterns that simply don't make sense based on our current knowledge. This brings us to yet another strange behavior of supermassive stars, the presence of unexplained spectral features. Imagine looking at that precise barcode of light and dark lines and finding extra lines, or lines that are in the wrong place, or lines that change in a way we can't explain with the physics we currently understand. These are the puzzling anomalies that occasionally pop up in the spectra of some supermassive stars, frustrating and exciting astronomers in equal measure. They are like cryptic messages from the deep cosmos, hints that there are processes at play in these extreme stars that we haven't yet figured out. What could cause these bizarre spectral features? One possibility is that they point to elements or isotopes in the star's atmosphere that we wouldn't expect to find there, perhaps brought up from deeper layers through unusual mixing processes or created by exotic nuclear reactions. Think of it as finding a rare ingredient in a recipe that shouldn't be there. Another explanation could be that the star's extreme conditions, those crushing pressures, intense magnetic fields, or rapid rotation are affecting how atoms absorb or emit light in ways that aren't captured by our current theoretical models. The physics of matter and radiation in such extreme environments can be incredibly complex, or perhaps these features are caused by interaction with surrounding material, like gas and dust from a companion star or a recent mass ejection event, creating unique signatures as the light passes through this external envelope. Sometimes these unexplained features aren't static. They might change over time, strengthening, weakening, or shifting in wavelength. Tracking these variations provides even more clues, suggesting dynamic processes are at work. These spectral anomalies are more than just curiosities. They are active areas of research because they could be the first hints of new physics or completely unexpected stellar phenomena. A persistent, unexplained spectral line could potentially lead to the discovery of a new type of nuclear reaction happening in the star's core, or reveal the presence of an incredibly strong magnetic field acting in a way we hadn't predicted, or even point to the existence of a previously unknown elementary particle influencing the star's interior. They are the frontiers of our ignorance about these fascinating objects, urging scientists to develop new theories, build more sophisticated models, and design the next generation of telescopes to gather even more detailed and precise spectroscopic data. Every time we analyze the light from a supermassive star and find one of these puzzling features, it's a powerful reminder that the universe is still full of mysteries, and these cosmic giants in their bizarre and extreme lives hold some of the keys to unlocking them. Imagine the heart of a galaxy, a bustling, crowded downtown filled with billions of stars all packed relatively close together. At the very center of most galaxies, including our own Milky Way, lurks a supermassive black hole, a gravitational monster millions or even billions of times the mass of our Sun. It's a chaotic, extreme environment, and guess what? Supermassive stars appear to play a significant and sometimes peculiar role in these galactic nuclei. Their presence in such close proximity to a supermassive black hole adds another layer to their already strange behavior. These regions aren't like the quiet suburbs of a galaxy where stars have plenty of elbow room. They are incredibly dense star cities where gravitational interactions are frequent and dramatic. So, how do these giants behave when they're practically orbiting a cosmic drainpipe? For starters, the intense gravitational pull of the central black hole can significantly influence the supermassive stars around it. Their orbits can be dramatically altered, becoming highly elongated or even flung out of the galactic nucleus altogether. This gravitational dance can also affect their internal structure and potentially trigger pulses or other instabilities as they are stretched and squeezed by the black hole's tidal forces. Think of how the moon's gravity causes tides on Earth, but on a scale so extreme it could deform a star. Furthermore, the powerful radiation and winds from the supermassive stars themselves can interact with the material swirling around the black hole, potentially influencing the rate at which the black hole feeds on gas and dust. This can impact the brightness of the galactic nucleus, sometimes causing it to flare up dramatically as more material falls into the black hole's maw. Then there's the possibility of truly destructive encounters. While direct collisions between stars are rare even in dense galactic nuclei, the near misses and strong gravitational interactions can have violent outcomes. A supermassive star passing too close to the central black hole could be torn apart by the immense tidal forces, a process known as tidal disruption. The shredded stellar material would then form a glowing stream of gas as it falls into the black hole, creating a powerful flare of light that astronomers can sometimes detect. These events are incredibly energetic and provide a dramatic illustration of the power of the central black hole and the precarious existence of stars in its immediate vicinity. The supermassive stars in galactic nuclei are therefore not just passive residents. They are active participants in the dynamic, sometimes violent, environment around the central black hole. their strange behaviors amplified by the extreme gravitational conditions of the galactic downtown. So, what does the future hold for our quest to understand these cosmic enigmas? The study of supermassive stars is an incredibly active and exciting field, constantly pushing the boundaries of our knowledge and technology. As we've seen, many of their strangest behaviors are still shrouded in mystery, demanding new observations and more sophisticated theoretical models. Fortunately, the future of astronomy is bright, with several upcoming missions and telescopes poised to revolutionize our ability to study these distant giants. Think about the next generation of space telescopes currently in development or being planned. Missions like the European Space Agency's Euclid telescope, which will map the large-scale structure of the universe, might uncover new populations of massive stars in distant galaxies. And future large ground-based observatories with their enormous mirrors will gather more light than ever before, allowing us to peer farther into the universe and collect more detailed spectra of these faint, distant objects. These new instruments will provide the crucial data needed to test our current theories about supermassive star formation, evolution, and death. They will help us find those elusive hydrogen-poor stars, detect the faint light from potential failed supernova, and perhaps even finally confirm the existence of those theoretical Thorne-Zitkow objects. Beyond just finding new stars, these telescopes will offer unprecedented detail on their spectra, allowing us to refine our measurements of their temperatures, compositions, and magnetic fields, shedding light on those unexplained spectral features. They will also be vital for observing the aftermath of supernova explosions, providing more detailed data on the remnants and helping us distinguish between different types of stellar deaths, including those hypothesized hypernova. Furthermore, observatories dedicated to detecting gravitational waves, like the Laser Interferometer Space Antenna, or LISA, which is a planned space-based detector, could potentially detect the gravitational ripples from the formation of black holes from the collapse of supermassive stars, offering a completely new way to probe these events. The key questions guiding this research remain profound. How do stars get this massive in the first place? What are the precise mechanisms driving their incredible mass loss and violent pulsations? Which of these giants end their lives as black holes without a bang, and which explode as the most powerful supernova? What exotic remnants might they leave behind? How did the very first supermassive stars influence the early universe? These are the cosmic riddles that the next generation of astronomers, using the next generation of powerful telescopes and theoretical tools, aim to solve. It's a journey of discovery that promises to continue revealing the bizarre and wonderful nature of the most extreme stars in the cosmos. So, keep your eyes on the skies and stay curious about the incredible lives and deaths of supermassive stars.